In mathematics, the operation of substitution consists in replacing all the occurrences of a free variable appearing in an expression or a formula by a number or another expression. In other words, an expression involving free variables may be considered as defining a function, and substituting values to the variables in the expression is equivalent to applying the function defined by the expression to these values. A change of variables is commonly a particular type of substitution, where the substituted values are expressions that depend on other variables. This is a standard technique used to reduce a difficult problem to a simpler one. A change of coordinates is a common type of change of variables. However, if the expression in which the variables are changed involves derivatives or integrals, the change of variable does not reduce to a substitution. A very simple example of a useful variable change can be seen in the problem of finding the roots of the sixth-order polynomial. Sixth-order polynomial equations are generally impossible to solve in terms of radicals. This particular equation, however, may be written. Thus, the equation may be simplified by defining a new variable x3 equals u. Substituting x by into the polynomial gives which is just a quadratic equation with solutions. The solutions in terms of the original variable are obtained by substituting x3 back in for u. Then, assuming that x is real, simple example. Consider the system of equations where n are positive integers with. Solving this normally is not terrible, but it may get a little tedious. However, we can rewrite the second equation as making the substitution reduces the system to solving this gives or back substituting the first-ordered pair gives us, which easily gives the solution back substituting the second-ordered pair gives us, which gives no solutions. Hence the solution that solves the system is. Formal introduction. Let be smooth manifolds and let be a diffeomorphism between them, that is a times continuously differentiable, bijective map from to with times continuously differentiable inverse from to. Here may be any natural number, or the map is called a regular coordinate transformation or regular variable substitution, where regular refers to the nessive. Usually one will write to indicate the replacement of the variable by substituting the value of n for every occurrence of. Other examples. Coordinate transformation. Some systems can be more easily solved when switching to cylindrical coordinates. Consider for example the equation. This may be a potential energy function for some physical problem. If one does not immediately see a solution, one might try the substitution given by. Note that if runs outside a length interval, for example, the map is no longer bijective, therefore should be limited to, for example. Notice how is excluded, for is not bijective in the origin. Then, replacing all occurrences of the original variables by the new expressions prescribed by and using the identity, we get. Now the solutions can be readily found. So or, applying the inversive shows that this is equivalent to while. Indeed we see that for the function vanishes, except for the origin. Note that, had we allowed, the origin would also have been a solution, though it is not a solution to the original problem. Here the bijectivity of is crucial. Note also that the function is always positive, hence the absolute values. Differentiation. The chain rule is used to simplify complicated differentiation. For example, to calculate the derivative the variable x may be changed by introducing x2 equals u. Then, by the chain rule, so that where in the very last step u has been replaced with x2. Integration. Difficult integrals may often be evaluated by changing variables. This is enabled by the substitution rule and is analogous to the use of the chain rule above. Difficult integrals may also be solved by simplifying the integral using a change of variables given by the corresponding Jacobian matrix and determinant. Using the Jacobian determinant and the corresponding change of variable that it gives as the basis of coordinate systems such as polar, cylindrical, and spherical coordinate systems. Differential equations. Variable changes for differentiation and integration are taught in elementary calculus, and the steps are rarely carried out in full. The very broad use of variable changes is apparent when considering differential equations, where the independent variables may be changed using the chain rule, or the dependent variables are changed, resulting in some differentiation to be carried out. Exotic changes, such as the mingling of dependent and independent variables in point and contact transformations, can be very complicated but allow much freedom. Very often, a general form for a change is substituted into a problem and parameters picked along the way to best simplify the problem. Scaling and shifting. Probably the simplest change is the scaling and shifting of variables. That is, replacing them with new variables that are stretched and moved by constant amounts. This is very common in practical applications to get physical parameters out of problems. For an nth-ordered derivative, the change simply results in where this may be shown readily through the chain rule and linearity of differentiation. This change is very common in practical applications to get physical parameters out of problems. For example, the boundary value problem describes parallel fluid flow between flat solid walls separated by a distance delta. Micro is the viscosity and the pressure gradient, both constants. By scaling the variables, the problem becomes where scaling is useful for many reasons. It simplifies analysis both by reducing the number of parameters and by simply making the problem neater. Proper scaling may normalize variables, that is, make them have a sensible unitless range such as 0 to 1. Finally, if a problem mandates numeric solution, the fewer the parameters, the fewer the number of computations. Momentum versus velocity. Consider a system of equations for a given function. The mass can be eliminated by the substitution. Clearly this is a bijective map from 2. Under the substitution, the system becomes Lagrangian mechanics given the force field. Newton's equations of motion are. Lagrange examined how these equations of motion change under an arbitrary substitution of variables. He found that the equations are equivalent to Newton's equations for the function, where T is the kinetic, and V the potential energy. In fact, when the substitution is chosen well, these equations are much easier to solve than Newton's equations in Cartesian coordinates.